All right, welcome back. We are going to be finishing up Chapter 16 with Section 4, which is covering gluconeogenesis as well as the regulation of gluconeogenesis. So again, if you remember in the last lecture, we were talking about if we deplete all of our glucose stores as glycogen and we deplete all of our free glucose, or we have no glucose 6-phosphate, and then the cell would then need to synthesize its own glucose. So glucose can be synthesized from a number of different precursors, and we'll get to that in just a minute. But again, here is our learning objectives. You want to be able to discuss the differences in glycolysis and gluconeogenesis, how gluconeogenesis is regulated, why certain metabolites would trigger gluconeogenesis or stop gluconeogenesis. Summarize gluconeogenesis as an overall reaction, so consider how many ATP are consumed to make one molecule of glucose. And then explain why pyruvate must first be converted to oxaloacetate before converting to PEP. Alright, so basically, just like I said, so when dietary glucose and glucagon has been exhausted, glucose can be synthesized from non-carbohydrate precursors. This occurs primarily in the liver, but sometimes can happen in the kidney. A number of metabolites from glucose metabolism can be used to make glucose. However, all things must go through the citric acid cycle intermediate oxaloacetate, which we see right here. And we'll talk about why in just a minute. Fatty acid metabolic intermediates cannot be used as precursors of glucose synthesis. However, their breakdown generates much of the ATP that is needed to power gluconeogenesis. And if you think about it, if we're burning fatty acids in order to generate ATP, then obviously we must have depleted all of our glucose. So it makes sense that we couple fatty acid breakdown with gluconeogenesis in order to help generate or restore some of our depleted ATP stores. So most of the reactions in glycolysis most of the reactions in gluconeogenesis are the reverse of glycolysis. So they share many of the same enzymes and metabolite intermediates. However, 3 of the enzymes in glycolysis have such a large negative delta G that we have to utilize different enzymes. And so these 3 enzymes, not surprisingly, are hexokinase, phosphofructokinase, that's spelled wrong, and pyruvate kinase. So to go from pyruvate to PEP, using pyruvate kinase, we have to bypass that, and we do that with 2 steps. We also have to bypass phosphofructokinase, and you'll see how we do that there, as well as glucose 6-phosphate to glucose with hexokinase must be bypassed with a different enzyme. You will notice that phosphoglycerate kinase does not need to be bypassed in gluconeogenesis because our delta G was near 0 in this step. So this one is actually freely reversible, even though we generated ATP in glycolysis and gluconeogenesis, we burn a molecule of ATP. Okay? So pyruvate, to be converted back to PEP, is done in 2 steps. And the reason is because this was such a high, going from PEP to pyruvate in glycolysis generated a large negative delta G. I believe it was about negative overall. Oh, it's in here in the book. Yeah, so it's about negative 22.6 kilojoules per mole. And so we went from a very high energy yielding molecule to a very low energy molecule. So to go backwards from pyruvate to PEP, we must first make a high energy intermediate molecule, which is this oxaloacetate. So by doing this carboxylic reaction, we have to couple it with ATP dephosphorylation in order to add an HCO3 molecule or what ends up becoming a CO2 unit onto pyruvate to make oxaloacetate. So now this molecule is high energy, and upon decarboxylation and using GTP to phosphorylate, we end up making these two steps together, coupled, give us a delta G of negative 22.6. I'm sorry, this one is 26.4. I was looking at the wrong figure. But this is from figure in your book, 16.21, if you want to look at those energies. Okay? So by first making this high energy intermediate and then the decarboxylation, we can generate enough energy to get back to our PEP. Again, we're going to burn a molecule of ATP in this step, as well as a molecule of GTP, in order to generate this PEP molecule. Now, what's interesting is oxaloacetate is only formed in the mitochondria. So PEP, now in the mitochondria is where oxaloacetate is formed. However, the rest of gluconeogenesis must occur in the cytosol. All right, so we're in the cytosol, here we're on the mitochondria. So in order to cross the mitochondrial membrane, PEP must be first transported into the mitochondria, and then it can be transferred, or it can be transformed into oxaloacetate. However, oxaloacetate cannot freely be transported across the membrane, and there's no protein that can help transport oxaloacetate. I'm just going to call it OXA. Okay, so OXA must first be transformed into aspartate or malate. Both of these utilize enzymes. Malate dehydrogenase has to utilize NADH in order to do this oxidation reduction reaction to make oxa into malate. However, aspartate utilizes an amino transfer reaction to do that. Once oxaloacetate is formed into either malate or aspartate, it can then be transported across the mitochondrial membrane into the cytosol, and then can be converted back into OXA. Once it's converted back into OXA, it can then be transformed into PEP and then utilized in gluconeogenesis. So we can either make OXA into PEP on this side and transport, or we must first transport it as malate and then transform back to OXA and then undergo the rest of gluconeogenesis. Hydrolytic reactions then bypass the other irreversible reactions of the glycolytic glycolysis reaction. So in gluconeogenesis, FBP, fructose 1,6-bisphosphatase, hydrolyzes FBP into fructose 6-phosphate. You can see our delta G is nowhere near as negative as it was with PFK. And again, this is instead of using a phosphate group to catalyze this, instead of doing phosphate group transfer, we are actually just hydrolyzing, so we're creating an inorganic phosphate. Then we can isomerize freely F6P to G6P. Then glucose 6-phosphatase is used to hydrolyze off the other phosphate group on G6P to make glucose. This is the same enzyme that is used in glucagon or glucogen dephosphorylation when we get fructose 6-phosphate from glucogen. Overall, this is going to cost us 6 ATPs in order to convert 2 pyruvate to 1 glucose. So we utilize 2 ATPs with this enzyme. So it takes 2 pyruvate, so we do this twice. So it's 1 ATP per pyruvate with PEPCK. We also have to burn an ATP molecule with the FBPase and the glucose 6-phosphatase in order to couple the reaction and make that go forward. And then if you remember here, between PEP and FBP with phosphoglycerate kinase, we're going to burn another molecule of ATP in this reaction steps here. Okay, so remember that's just that same enzyme in glycolysis. So how do we regulate gluconeogenesis? Also helps us regulate glucose. So remember, fructose 2,6-bisphosphate activates PFK1. So fructose 2,6-bisphosphate will activate PFK1, but will inhibit at the same time FBPase, which makes sense because if you remember, fructose 2,6-bisphosphate is released from PFK2, which is activated by insulin. So insulin is released when there's high blood glucose. So if there's high blood glucose, then we want to we want to increase glycolysis while decreasing gluconeogenesis, because why do we need to make glucose if we already have high glucose levels? Acetyl-CoA activates pyruvate carboxylase. So acetyl-CoA is an intermediate in lipid or fatty acid metabolism. So if we're burning fatty acid in order to make ATP and then we're giving off acetyl-CoA as a byproduct in those reactions, then this would be a good indicator that we have low blood glucose or low glucose being metabolized in glycolysis. So if we're burning fatty acids in order to make ATP, then we must not have any glucose, and so we need to do gluconeogenesis. Pyruvate kinase is inhibited in the liver by alanine, which is also a gluconeogenic precursor. So if we're undergoing gluconeogenesis, then obviously pyruvate kinase, which is this enzyme, does not need to be working, and it would save us a few steps if we could go from PEP to glucose versus starting from pyruvate to glucose. So by shutting off pyruvate kinase, we can stop glycolysis here and then just go in the reverse. Enzyme expression is also a great way to control both glycolysis and gluconeogenesis. So insulin, remember insulin is present when there's high blood sugar. So this inhibits the expression of PEPCK, right, which is that enzyme that helps transfer or helps change pyruvate back to PEP. And then also high levels of CAMP, which is a byproduct of the citric acid cycle. So high levels of CAMP promotes the expression of PEPCK, which is here, FBPase, as well as glucose 6-phosphatase, and then represses expression of glucokinase, PFK1, and PFK2. All right, so if we have high CAMP, then that is a byproduct of both fatty acid metabolism as well as the citric acid cycle, and also indicates that we have low ATP. And so we would want to so it would indicate that we have low glucose, and so we need to start making more glucose. All right, so that is the end of this chapter. So remember, if you went to this one first, there's another video lecture on glycogen metabolism that you need to watch in order to be ready for class. I just wanted to break the two lectures up so that it was a little more manageable when you're studying, as well as going over the material. Please feel free to post any questions you may have on Facebook or email me, and I will see you in class the next time we meet. All right, I hope you guys have a great day. Oops, let's go. I will...